Good morning and welcome to this lecture on sound in structural vibration. We were discussing the gamma issue, okay, which is square root of k square minus k0 square, okay, and real values of gamma. Then we said gamma must be a positive real number. If gamma turns out to be imaginary, then gamma should be of the form negative imaginary times some number. Okay. So we have to look at how to make a continuous branch for gamma and how to find such a branch that this is also satisfied. Okay. But let us just first look at the square root function in the complex plane. Okay. So let us consider square root of k square minus k0 squared. Okay. I am deliberately using k's. Okay. In a textbook you will probably find it as z square minus z0 square. Okay. But I would like you to get used to k now being the complex number, so I am using this. Okay. So what is this? This is square root of k minus k0 into square root of k0 plus k plus k0. Okay. So let us draw the complex plane. K0s is a real number. Okay. So I have k0 here and I have minus k0 here, minus k0 and a k0, and so this is the real axis, this is the imaginary axis. Okay. So let us say my k is somewhere here, a complex number, k is here. Okay. So k minus k0 is this vector and k plus k0 is this vector. Now let us describe those vectors in terms of phasor notation, amplitude and angle. Okay. So let me say that my k minus k0 is equal to some amplitude e to the power of I phi. So this angle is my phi. Okay. That means square root of k minus k0 is equal to k minus k0 half e to the power of I phi by 2. Okay. Now I will define the limits of phi. So let us say that 0 less than equal to phi less than equal to twice pi. Okay. Phi ranges between 0 and 2 pi. Okay. Similarly, k plus k0 is equal to amplitude of k plus k0 e to the power of I theta. So this angle is theta. Again 0 less than equal to theta less than equal to twice pi. Okay. Now, okay, so similarly square root of k plus k0 is equal to k plus k0 half e to the power of I theta by 2. So this square root function k square minus k0 square is equal to amplitude of this thing k minus k0 k plus k0 e to the power of I theta plus phi by 2. Okay. So these are real positive numbers, so they don't have a significant effect here, they are just amplitudes. The actual continuity is decided by this function, okay, I theta plus phi by 2, and how is that we will see. So let us see now. Okay, so here at this location, if I take my k very close to the real axis, then this is the one vector and the other is this vector, one from k0, one from minus k0. So I can say my phi is 0, theta is 0. Okay. If I reach this point, if I come here, then phi has come, half circle. So phi will be pi and theta is still 0. If I come here, okay, even theta has come half circle. So phi is pi and theta is also pi. Okay. And if I go just below the negative real axis, here also phi is pi and theta is pi. If I come here between, then this theta has gone full circle, whereas phi is still pi. So I get phi equal to pi and theta equal to 2 pi. And if I just go below the real axis, positive real axis here, I get phi has gone full circle, theta has gone full circle, so phi is twice pi, theta is also twice pi. Okay. Now we want to look at this term theta plus phi by 2. Okay. So if I do that here, I get e to the power I0, which is 1. Here e to the power I twice pi plus twice pi by 2, which is e to the power I twice pi, which is also 1, no problem. Okay. But here I get e to the power of I pi by 2. Here I get e to the power I 3 pi by 2. So this is actually equal to I, this is equal to minus I. So if I move across here, okay, if I move across that line, I get a jump. I get a jump in the function value. So that region is not allowed, I can't cross. Okay. Now if we go back to here, phi and theta are both pi across, so I am continuous. So I get e to the power of I pi, e to the power I pi, which means what? If I have a contour, if I have some contour, it can't cross the region here because the function takes a jump. Okay. I can do this, I can take a contour which goes around, I can do this. But I can't do this, I can't take a contour, it goes and cuts this line. So this line is called a branch cut. Okay, this line is called a branch cut, and it happens to be between the values plus k0 and minus k0. Okay. I have given a series of lectures on integration on the complex plane, okay, a short series of about 24 half-hour lectures, where this branch cut has been explained in great detail. So and these are there on NPTEL or YouTube, so you can look at it. Okay, it's something like a series on integration in the complex plane. Okay, and if you type my name, you will get this on YouTube also. So you can see I have discussed branch cuts in great detail. Okay, so I won't repeat the entire deal here. So that's the branch cut. Okay, now this branch cut is unique to this choice of theta values, theta phi values. Okay, so now let us see here, if I choose K0 minus K0, let's say my K is here, this is K minus K0, K plus K0. Okay, now I will choose for phi, I will choose the same limits, 0 twice pi, but theta I will choose like this. I've chosen a different range for theta. Okay, so what does that do? So I'll quickly look at it here. So phi is still 0 here, theta, okay, if I take a point close by, this is one vector and that's the other vector, phi is 0, theta is also 0. Okay, so if I come over here, this is phi, of course, this is theta. Okay, now phi has come to pi. Now theta is still 0. Okay, I am minus pi here, I am minus pi here, and I am so 0 over here. Okay, so theta is still 0. If I come here, my phi is pi and theta is pi. Okay, because theta has gone full circle, it's pi. And just below I have phi still equal to pi, but theta jumps minus pi. Okay, and here my phi is still pi and theta is 0, and here phi is twice pi just below, and theta is equal to 0. Okay, so if I look at this expression now, I look at this expression, I get e to the power I0 above, which is 1. I get e to the power of I twice pi by 2, which is e to the power I pi, which is minus 1. Okay, so it's different. Here theta phi are same. Okay, I get e to the power I pi by 2 on top and bottom. No problem here, but here I get e to the power I pi above, which is a minus 1, and I get e to the power I0, which is a 1. So you can see now that with this choice of theta phi, I have a discontinuity here. Okay, so the branch cut happens from K0 to plus infinity, okay, and from plus infinity it comes to minus k0. So that means what? I can have a contour integral which goes and does this, but I can't have a contour integral which goes and does this. I can't cross this line. Same here, I cannot have a contour which crosses that line. So that's a branch cut. Okay. Now there are several ways to do cuts, I said. Okay, so let's take one more, and these will be used in the problem. Okay, they will come of use in the thought process for this problem. So now we said gamma has, you know, issues for bounds, right? Gamma real, then gamma should be positive, and gamma is what? Square root of k square minus k0 square. Okay, and mind you, if you remember, k is the integration variable. Integration variable. That means the integrals are with respect to dk, and k is going to be made complex. K becomes complex in the plane. Okay, and to carry on this idea, when gamma becomes imaginary, gamma must be negative, imaginary, minus I times something. Okay. So the previous cuts I showed, branch cuts, they are just to show that how to take cuts for a branch. Okay, and what lines are not allowed, what are lines are allowed that you can cross. Okay. Now here I am going to show you a region in the complex plane where this issue will be satisfied, where this point and this point will be satisfied. Okay, it's important to emphasize that this should be satisfied only when k is real. Okay, okay, because the integral I want is going to be on the real line. Okay, that's the integral I want. Anything else is extra. Okay, in the complex integration I have shown you that you get extra portions which have to be evaluated and used along with Cauchy residue theorem. However, the one integral I want is actually moving on the real axis. So when k is moving on the real line, these should be satisfied. That's the important part. Okay. Once k has moved into the complex domain, something can happen, but we are not worried about that. Only when it is moving on the real line, I want these criteria to be satisfied. Okay. So now let us see one branch here. I have a k0 and I have a, let's see, minus k0. So now I have the complex number k sitting over here with its two vector components k minus k0 and k plus k0. So k minus k0 square root, or let's say k minus k0 to begin with, I will define using k minus k0 magnitude e to the power I theta, where theta now goes from pi by 2 5 pi by 2. Okay. So that results in a cut like this. Okay. So my theta moves from pi by 2 here and it goes around and comes to 5 pi by 2. Okay. Similarly, at minus k0, I have k plus k0, which is given by magnitude k plus k0 e to the power I phi, and phi now takes values between 3 pi by 2 to 7 pi by 2. So it begins here, goes around and comes back here. Okay, it begins here, goes around and it comes back here. Whereas the first fellow begins here, goes around and comes back here. Okay, so now let us look at a region over here. So if I have to redraw, okay, so here my theta is going to be 1 pi by 2, 2 pi by 2, 3 pi by 2, 3 pi by 2. Okay, sorry. So it is pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2. 4 pi by 2, it is 2 pi. Okay, right here, just above the real axis. Okay. Now what is phi over there? Phi is right here. Phi is 3 pi by 2. So here it will be 4 pi by 2. So 2 pi. Okay. So if I take the half of that, I get e to the power of I twice pi, I get a 1, which is equal to 1. All the way here, it's 1. Okay. Now just below right here, okay, phi is still equal to twice pi, theta is still equal to twice pi, so I get e to the power of I twice pi, so no problem here. Okay. Now suppose I cross and come here, okay, then theta is 2 pi by 2, which is pi. Theta is pi here. If I consider a point, theta is pi over here. Okay, and then what is phi? Phi is 3 pi by 2, 4 pi by 2. Phi is 2 pi. Okay, and what is the angular function? I theta plus phi by 2 gives me I 3 pi by 2. Okay, so you can see that there is a discontinuity across this line. Okay. So now you can also see that I have k0 over here and minus k0 over here, okay. So, and k is what I am looking at on the real axis, right. So, when k is here, okay, I get for this function which is square root of k square minus k0 square, the combined function, I get a magnitude and e to the power of I twice pi here in this region, okay, and that region is what, k greater than k0, which means gamma is real. So, when gamma is real, I get an amplitude, okay, n to e to the power I twice pi. So, it is a real positive number. Whereas, when I come over here, I cross over and come here at this location, k is real of course, but magnitude of k is less than k0. So, gamma becomes imaginary. So, what values does it have? Here I get gamma is again some amplitude, but in addition I get a negative I. I have e to the power of I 3 pi by 2. So, I get a negative I. So, it is a negative imaginary number. Okay. So, the same will be the story here also. Okay. In this region you will get a negative imaginary number, and here again you will get a positive real number. Okay. So, with this kind of a cut going vertical, I not only give a continuous branch for the function gamma, okay, but I also satisfy these two criteria when k moves on the real axis for the integral that I want. Okay. So, this is very important. So, we will be looking at this cut. This is the cut we will be looking at. Okay. However, there is one more cut which will actually give you the same uniqueness, continuous behavior of the branch, and these two criteria satisfied. I will show that in the next class. Okay. Time is running out. Thank you very much.